Hello students, Mr. Courtney here. In this video, I'm going to be talking about the gas laws, and we're going to be paying attention to the molecular theory, or the kinetic molecular theory to be more precise. So we're going to describe a gas at the submicroscopic level in terms of pressure, volume, and temperature. And we'll use the kinetic molecular theory to explain the behavior of gases and apply Dalton's law of partial pressure. The kinetic molecular theory is a model that is used to explain the behavior of an ideal gas. It helps us to explain the diffusion of gases, which is the movement of the gases or the gas molecules from an area of high concentration to an area of lower concentration. It also explains the ability of a gas to spread out and fill a container. We then think of Brownian motion, which is the observable movement of particles due to collisions with moving molecules. Now, based on the kinetic molecular theory is based on the assumption about the behavior of the individual particles in a gas. That is, how do these gas molecules behave by themselves? So that's what we're going to be focusing on here. The theory explains, or it helps to describe the differences between gases, liquids, and solids, and it also helps to explain the gas laws, which we will talk about later on also. So the assumptions of the kinetic molecular theory. So first we're going to look at the size of the particles compared to the distance between them. So when we talk about the size of the particles, we say that they're negligible. They're so small compared to the distance between them. This explains why gases are compressible. So there's a relatively large space between these particles. So these spaces can be filled by pushing these molecules closer together. That's why gases are compressible. So compressibility is a measure of how much the matter can decrease under pressure. How much can these particles be pushed closer together? And gases are easily compressed because of the large spaces between these particles. The second assumption is that there are no attractive or repulsive forces between the particles. Because there are no attractive or repulsive forces between these particles, they will not be able to repel or attract each other. So the gases will take on the shape and fill the volume of the container. So the particles are free to move. There are no restrictions to their movement. And if these particles are free to move, then they can also expand. So that explains why gases will take the shape of the container and fill the entire volume of it. So here we see that these particles are in constant random motion and the collisions are perfectly elastic. What is it we mean by we say these collisions are perfectly elastic? It means that there is no energy loss due to the collisions. So even though they collide with the walls of the container or with each other, there is no loss of energy. And because these particles collide with the walls of the container, they also create pressure. And we'll talk about pressure a little bit later on. So the variables that describe a gas talk about pressure, volume, temperature, and moles, which is a number of moles. So we're going to look at these variables in details as we go along in this lesson. First, we start off with pressure. Pressure is the force per unit area. That is force divided by area. How much force do these particles hit the walls of the container with? What area do they come in contact with? The more particles you have hitting the same area, the greater the pressure. The more force you have on that area, the greater the pressure. Pressure is measured using a barometer, and it can be measured in atmospheres, millimeters of mercury, or torr, and also in pascals, which is the SI unit, which is the standard unit. So most times you'll see pressure being measured in pascals. But in this unit, we're going to use it in atmospheres. So here we see that these particles, again, are in constant random motion. And because they collide with the walls of the container, they exert a force on the walls. And based on the size of the area and the size of the force, the pressure is determined. More particles hitting the walls of the container increases pressure. Particles moving at a faster velocity hits the walls of the container with greater force, which increases the pressure also. Okay, so here we're going to talk about, just do some conversions. We're going to convert 0.890 atmospheres to millimeters of mercury. So we start with our 0.89 atmospheres. We want to go from atmospheres to millimeters of mercury. We know that there are 760 millimeters of mercury in one atmosphere. This is what we determine from here. 760 millimeters of mercury is equal to 1 atmosphere. So here our atmospheres will cancel, which leaves us with the unit that we want of millimeters of mercury. We get 676 millimeters of mercury. In the second example, we want to convert the same 0.89 atmospheres to pascals. So we have to look, what is the relationship here? Okay, and we know that 0.89 atmospheres can be converted to pascals. In this case, we're going to go to kilopascals. There are 101.325 kilopascals in one atmosphere, as we determined from this here, from this relationship we're given. 101.325 kilopascals in one atmosphere. Again, our atmospheres will cancel, and we get 90.2 kilopascals, or we can convert it to pascals as we were asked, and get our answer. Temperature. Now, temperature is a measure of the average kinetic energy of the individual gas particles. That is, how fast are these gas particles moving? Because remember, kinetic energy is equal to half mv squared. So the greater the velocity of these particles, the greater the kinetic energy. If we increase the mass, same velocity, we're going to also increase the kinetic energy. So at the same temperature, heavier gases move slower than lighter gases. All right, so if temperature is a measure of the average kinetic energy, so particles at the same temperature should have the same kinetic energy. So the heavier particles would be moving slower than the lighter particles, because the lighter particles have to make up for that extra mass. So they're going to be moving faster to maintain that same kinetic energy. Temperature is going to be measured in Kelvin or Celsius. We do not really use the Fahrenheit in science, so you're going to either see it in Kelvin or Celsius. And the reason being, it's easier to convert between Kelvin and Celsius than to go from Kelvin to Fahrenheit, or Fahrenheit to Kelvin, or Fahrenheit to Celsius, or from Celsius to Fahrenheit. It's an easier conversion to go from Celsius to Kelvin or Kelvin to Celsius. So we see that our Kelvin temperature is equal to a degree Celsius plus 273, and our temperature in Celsius is equal to the Kelvin temperature minus 273. So now let's look at the effect of heating or cooling the gas particles or gases. We're going to see what that causes in terms of kinetic energy, the number of collisions, and pressure. When we say number of collisions, how often do these particles collide with each other? So if you heat, you're going to increase the kinetic energy, because temperature is a measure of the average kinetic energy. Heating increases temperature. Once you increase temperature, the particles have more energy. They start moving faster. So the kinetic energy increases. And if the kinetic energy increases, then the collisions will also increase. That is, the collisions with each other and the walls of the container. Now, if you increase the number of collisions against the walls of the container on the same area, you're going to increase your pressure. Now, if you do the opposite, which is you cool, that means you're going to lower the temperature. You're going to slow these particles down. They have less energy, so the kinetic energy decreases. The velocity decreases, so the kinetic energy decreases. Once that decreases, then the number of collisions will decrease. They will not collide with each other as often, or with the walls of the container as often as before. And if they do not collide with the walls of the container as often as before, then that's going to cause a decrease in the pressure. So here we see, if we heat or increase temperature, we cause an increase in pressure, number of collisions, and kinetic energy. And if we cool or decrease the temperature, we cause a decrease in the kinetic energy, the number of collisions, and the pressure. So here we see that temperature and pressure are directly related. That means if I increase temperature, I'm going to increase pressure. If I decrease pressure, if I decrease the temperature, I'm going to decrease pressure. So that's how they are related. They are directly related. So if I double the temperature in Kelvin, then I'm going to also double the pressure. That will result in a doubling of our pressure. All right, let's look at in terms of moles. Mole, when we talk about moles, the number of particles. How much of the substance do we have in the sample? So if you add a gas, that means you add in more gas, you're going to increase the number of particles. And if you increase the number of particles, you're also going to increase the number of collisions. If you think about it, you're in an empty room by yourself. You're in a room by yourself. Then two more people come in. What's the likelihood of you colliding with those people? That increases. Then keep putting more and more in the room. The more people that come into the room, the greater the likelihood of you having to meet them or collide with them. And that, as you increase the number of particles and increase collisions, pressure also increases. But if you remove the gas, you're decreasing the number of particles. There will be less collisions with each other and less collisions with the walls of the container. That will cause a decrease in pressure. So here we see the number of particles, or the moles of particles, and pressure are also directly related. So if I double the number of particles, then I'm going to double the pressure. So the number of particles and pressure are directly related. By doubling the number of particles, you're going to cause a doubling of the pressure. So volume talks about, or refers to the amount of space the gas particles occupy. So here we see we have varying volumes. We have a small volume and we have a larger volume here. So if we increase the volume, then we're going to decrease pressure, because we have the same number of particles, but they have to spread their force over a larger area. So that causes a decrease in pressure, because here they have a larger area to exert their force on. Whereas if you decrease the volume, you're decreasing the area that these gas particles have to exert their force on. So you're going to increase pressure. So here we see that volume and pressure are inversely related. That is, if you increase one, the other one decreases. Or if you decrease one, the other one increases. So if you cut the volume in half, you're going to double the pressure. So let's say we started with this volume here, and this is half of that volume. Then we expect the pressure in this container in B to be twice that of the pressure in container A. Now, the temperature of the gas increases when it is compressed and decreases when it expanded. In other words, as you increase pressure, the temperature of the gas will increase, and as you decrease pressure, when it expands, the temperature of the gas will decrease. So ideal versus real gases. So I've mentioned before ideal gases. Now we talk about what is an ideal gas and what is a real gas. Ideal gases are the gas that follows the kinetic molecular theory under all conditions of temperature and pressure. But sadly, these gases do not exist. We have real gases, and these gases can be liquefied or sometimes solidified. They behave like ideal gases at high temperature and low pressure. So we do not have ideal gases, we have real gases. But the real gases behave like ideal gases at high temperature and low pressure. And remember, an ideal gas obeys the gas laws, or the kinetic molecular theory, under all conditions of temperature and pressure. Whereas your real gases only obey these laws of the kinetic molecular theory at high temperature and low pressure. So at high temperature, the molecules have a high kinetic energy and little attraction for each other. So if there's little attraction for each other, then there's nothing really slowing them down. So they're going to keep on moving. At low pressure, the gas molecules are farther apart, which makes the gas less dense. And if it's less dense, there's less attraction and the volume is more negligible. So here we see why they're obeying these gas laws or the kinetic molecular theory, because there's little attraction at high temperature, and at low pressure the volume of the gas particles, the volume is negligible, which is one of the assumptions we stated in, or two of the assumptions we stated in the kinetic molecular theory. Now, the molecules of gases with high molecular masses are, they have complex shapes and they have polar attractions. That you have, remember, you have positive or negative regions in these molecules. They're going to interact more with each other. There's going to be some attraction between these particles, where because they're heavy or if they're complex shape or they're polar attractions, they do not follow the gas laws exactly. You can use more complex things like van der Waals forces to explain these. I will not be talking about this now. Now, the pressure exerted by a mixture of gases at constant volume and temperature is equal to the sum of the partial pressures. And that is called Dalton's law of partial pressure. If you have a mixture of gases, the total pressure is equal to the sum of the pressures exerted by the individual gases. So if I have two gases, then I'm going to add these two pressures of these gases together to get my total pressure. So if I have oxygen and nitrogen together, the pressure exerted by oxygen plus the pressure exerted by nitrogen will give me my total pressure. And that is true for any mixture of gases. As long as we know the partial pressure of each of these individual gases, we can find the total pressure. So this is P1 for our first gas, P2 our second gas, P3 our third gas, and we can continue going on. And as many gas we have, types of gases we have. Alright, so here we have an example which asks us to determine the total pressure for gas mixture that contains nitrogen and oxygen. Now, if the partial pressure of the nitrogen is 725 millimeters of mercury and the partial pressure of oxygen is 426 millimeters of mercury. So we have to find the total pressure. Pretty simple. Total pressure, since we have two gases, will be the partial pressure of oxygen plus the partial pressure of nitrogen. So we're going to add these two partial pressures together to get our total pressure. So the 426 millimeters of mercury, which is the partial pressure of oxygen, plus the 725 millimeters of mercury, which is the partial pressure of nitrogen. So we add these two values together, and that gives us our total pressure of 1151 millimeters of mercury. And there we have our answer for that one. Now, here we're told that the total air pressure is 760 millimeters of mercury. If 78% is nitrogen and 20% is oxygen, what is the partial pressure of these gases? So we're given the total pressure already, which is our 760 millimeters of mercury. But we're told 78% is nitrogen and 20% is oxygen. What is the partial pressure? So that means our 760 millimeters of mercury is equal to the partial pressure of oxygen plus nitrogen. So what we have to do is find what is 78% and 20% of 760. So to find the partial pressure of nitrogen, since nitrogen is 78%, or it exerts 78% of the pressure is due to nitrogen, we take 78% of 760 millimeters of mercury. That gives us 593 millimeters of mercury, because 78% of the total is exerted by nitrogen gas. For oxygen, we take 20%, we find 20% of that set total pressure, and that gives us 152 millimeters of mercury. So there we found our partial pressure due to nitrogen and our partial pressure due to oxygen. Now, some gases are often collected by displacement of water. So there's going to be some pressure exerted by the water vapor. So the sum of the gas pressure and the water vapor pressure is equal to atmospheric pressure. So to find the pressure of the gas, we need to subtract the pressure of the water vapor, or the water vapor pressure. And this just shows us the simple setup that we use. We heat our substance, whether it's potassium chlorate, manganese dioxide. So we heat it up, When the gas is produced, the gas will bubble through here. It will displace the water molecules. Now we can collect our gas. So the gas in here, or the pressure exerted here, will be a mixture of the gas pressure and the water vapor pressure. And these are going to be equal to atmospheric pressure. And knowing that, we can find the gas pressure by subtracting the water vapor pressure. So a sample of nitrogen gas is collected by the downward displacement of water from an inverted bottle. What is the partial pressure of nitrogen gas at 20 degrees Celsius if the atmospheric pressure is 752 millimeters of mercury? The water vapor pressure at 17.5 millimeters of mercury at 20 degrees Celsius. Now it's important to understand that the water vapor pressure varies with temperature. So you can be given a chart or you can be given it in the question. It's not a constant. It will vary with temperature. So we know that we have 752 millimeters of mercury. That's our total pressure. So that's the atmospheric pressure. So pressure of the water vapor plus the partial pressure of nitrogen will be equal to our 752 millimeters of mercury. We already know what the partial pressure of water vapor is. So to find out of nitrogen, the partial pressure of nitrogen, we subtract that 17.5 from our atmospheric pressure, which is 752, and that leaves us with 734.5 millimeters of mercury. So again, to find your partial pressure of a gas when it's collected over water or by the displacement of water, we must subtract the water vapor pressure at that given temperature to find our partial pressure due to our gas. All right, so this takes us to the end of this lesson. Until the next time, I'm out. Blessings.